Okay, guys. Remember last Okay, sorry. Am I recording? Yes. Okay, so last time I said I'm gonna confirm the quiz and the final exam. I mean the chapters that will be on the quiz and also on the final exam. However, it has not been decided yet. Um, So yes, I will keep you updated once I know. But for now, please focus on our coming exam, which is Penilaian 2. It is on week 15 and it is on chapter 3, 4, 5. You will have 3 questions, one question for each chapter. Okay? So kalau sempat kita akan ada revision. If not, I mean chapter 3, 4, 5 is quite, I wouldn't say easy lah, tapi I think you can do it. Kita dah banyak exercises on chapter 3 especially because we have been using chapter 3 punya knowledge up until now. So hopefully everyone still remembers the basic ones like the condition, net F equals to 0 or net F equals to MA. Those are the things that you need to really focus on. And free body diagram, of course. Nanti kita akan do a revision if sempat, insyaAllah. But until then, please do your own revision. You can always go through your web assigned questions, redo those questions. The web assigned displays the answer after it is due. So if you got it wrong, they will give you the answer and you can try to do the solution on your own ataupun tengok the hints and do a practice. The ebook is there for you to do practices as well. You're not limited to the questions in WebAssign. You can also design your own homework using WebAssign. It's free for you guys. You need to explore a bit lah if you want to do that. If not, just use the ebook. The ebook has questions, but not in the form of WebAssign lah. Dia macam textbook biasa, buat dalam buku lah, buku sendiri. And also the ebook also has examples. You can go through them as well, or you can go through my previous videos. They are all recorded and in my playlist. You know this already, right? Okay, so let's continue with chapter 8. We talked about the free body diagram for a rigid body that has the tendency to rotate. Now remember that we talked about equilibrium has to satisfy 2 conditions. The first condition is net in the F is equal to 0 and net in the torque should be equal to 0. So it has to not move linearly, either X, Y, Z, and it also cannot move rotationally, I mean in the rotational sense. So that is net in the torque equals to 0. When we when when you're given a diagram like this, and how do you know if it has a tendency to rotate or not? You look, the first thing that you should look at is whether it has a hinge, right? So if you have a hinge like a door, you know for sure it can have that rotational motion. Walaupun, even though that it is not going to complete, even though it's not going to complete the entire circle. What happened here? Where did it go? Jauhnya. Okay. Okay, I'm going to repeat myself here. So if there is a hinge, you know that there will be rotational motion, even though the rotational motion will not satisfy a full complete circle, but the movement of the door has some angle of, has some circular motion to it, right? Even though it does not make a full circle, we still consider it as rotational motion because it follows a radius and it has some angle. So that is how you identify if something has a tendency to rotate or not. But what if the object does not have a hinge? This is our next example. This object does not have a hinge, but how do I know that it has the tendency to rotate? Now, if this cable snaps, it is no longer supporting this beam, right? And if the cable snaps, what would happen to the beam? It would fall down. And the falling motion of this beam if it was not supported by the rope, is rotational. You can imagine it, this is the radius, and it goes down like this. Assuming it has this support over here, it is fixed, it's not a hinge, but if this snaps, the fixed support over here probably would not be able to sustain the beam because of its weight, right? Initially the beam is supported, the weight of the beam is supported by this rope and also like maybe a cement over here, but when this snaps, all the weight is distributed to this contact point ataupun the cement ke, or like screws, whatever, that keeps it in place. So this guy probably will not be able to sustain that weight and it snaps off, and when it goes down, it would fall in this motion because dia akan slowly crack away, right? If this thing immediately snaps, maybe it can just fall down, free fall. Who knows? But we're assuming that it moves like this. Okay, any questions about rotational motion in general from previous class? Or like if you have any burning questions that you want to ask me before we continue? So everyone's okay? Okay, I'm going to continue. Okay. So we need to know how to draw the free body diagram. I've given you a document in your WhatsApp. Please go through those examples. Some of them are easy, some of them are hard, but it's very crucial for you to understand how to do it. Okay, so let's go through this one. We have a beam and this guy is here. He is brave enough to stand on this beam because he knows that this rope is also supporting this beam. So we have this weight of the guy. We call this as weight number one, weight number two. And the weight of this beam is weight number one. What is the radius of weight number one? What is the radius of that force from the axis of rotation? Axis of rotation ni our contact point lah. Okay, even though we don't have a hinge here. What is the radius here? If you guys still remember.
R/2.
L/2.
L/2. So we don't have L here, but I'm assuming you guys are saying it's half the length of the beam, right? So if I'm going to call this as L, then W1 or weight number one is going to be L/2 because your mass is always going to be at the center point of your object. This was the approach that we used also in chapter 3. Your mass is, everything is concentrated in the center point of the object. And then we have tension because this is a string. This is normal stuff. And then we have our contact point that has the tendency to rotate. We have our contact point that has the tendency to rotate. And this is Rx and Ry. I'm just labeling it Rx and Ry. It is an unknown. We don't know which direction it actually is. It depends on how much Ry we have, how much Rx we have, and then from there, we can know what is our R once we solve what R is. And then we can know the angle of R by all this equation that we have learned before. So we have to solve for Rx and Ry to know these things. And then I would know, okay, is R like this? Is R like this? Or is R like this? We don't know. So that is what we're trying to solve. Okay. So moving on. So this is, we're going to call this as L/2, and the radius of L should be L. Sorry, the radius of T, tension, should be L. And the radius of this guy, we don't know. They called it L, they called it L2. It's over here. They called this as L2. So since we have L2, we have to distinguish the length, the regular length to this length. So we're going to call this L1, and this is L1/2. So L1 is the length of the beam, L1/2 is the radius of that guy standing on the beam, and L2 is the radius of the guy. Right, okay. So now we know that we have to write down our equation. We don't know the condition here. If it says it is in equilibrium, assuming that it is, because if it's not in equilibrium, it would be moving and this guy would die. So we're going to just say net torque in the zero. Net torque is equal to 0. And then we have our Ry and Rx, but Ry and Rx is at the point of contact. The radius is 0, therefore torque is non-existent for R. Okay, so Ry and Rx is at the point of contact. The R is 0, therefore torque is 0. So we're going to ignore this. So W2, L2 is moving this way. If this guy, if we remember the, I have this. Okay, let's try to remember how to find out whether it's clockwise or anti-clockwise, because we need to know what is the direction. So first of all, we identified the axis of rotation, right? Axis of rotation. I'm going to try to be more organized here. It's like all over the place. And then the radius for each force. Okay, and then this third step is to identify the positive and negative direction of this torque. So W2, the weight of this man, the axis of rotation is here, right? So my hand over here is my axis of rotation, assuming that it has the tendency to rotate. So I'm going to push this. The man is over here somewhat. I'm pushing it. It would rotate clockwise. So clockwise is negative or positive, guys?
Negative.
Negative, right? So our first equation is negative. And then the next one is weight 1 L1 over 2. The radius is L1 over 2. The force is weight 1. So I want to see, so center beam, if this guy snaps, if the, what do you call this, string snaps, it will fall like this, right? It's not going to fall like this. That doesn't make sense. It's going to follow the gravity, right? So I'm pushing this to represent weight. It is still moving clockwise. So that is a minus W1 L1 over 2. Alah, tak bestnya. Minus W1 L1 over 2. Okay. Next one, tension. So tension is that way. Remember, we need to know what is our perpendicular force. This guy is perpendicular. This guy is perpendicular. This guy is not. We need to know what is perpendicular to the radius or to the lever arm. So this becomes T sine theta. I can resolve it into these two components, but I'm only going to use the one that is T perpendicular to the beam. This is parallel. Parallel goes through the axis. Doesn't do much to us. So we want to know the perpendicular force to the beam. It has to be 90 degrees. So if I'm trying to imagine whether it is going clockwise or anti-clockwise, I push it in its direction. It's going to go up like this. This is my axis of rotation. This is my force. It's going up. So it's anti-clockwise. So that is going to be a positive T sine theta. The length is L1. Sama tak? T sine theta L1, betul. Minus W2 L2, betul. Minus W1 L1 over 2, sama. So this is how they got the equation. Okay, I'm sure you guys can do this by now. It's basically like almost like chapter 3, except that we have to know whether it's clockwise or anti-clockwise. That is their positive and negative. So AC and clockwise. So AC is positive, clockwise is negative. So that is for your torque. Now to have equilibrium, we need to satisfy two conditions, whether first one is torque, second one is force, or vice versa. Dua-dua kena kosong lah. So for force, we also need to solve it. So the X components in the X. Let's go through this diagram. So our net component in the X is going to be T cosine theta. This is going to be T sine theta. So the forces in the X, kumpul semua kat sini. Alah, dia tak buat kat sini pula. T cosine theta. This is T sine theta. So in our x direction, we have minus t cosine theta, positive rx, positive t sine theta, positive ry, minus w1 minus w2, the weights. Combine all your forces into the center. That is your free body diagram for forces. For torque, we don't combine them because we need to know what direction it contributes to, whether anti-clockwise and clockwise. So if kalau semua kat tengah-tengah, then there wouldn't be any movement lah. So kena ada that distribution, right? So torque, forces dia tak berkumpul, forces semua kat tengah. I'm going to skip this one. You guys have the document. You guys can go through it. If you have any questions, you can ask me as usual. Okay. This is an example in PBL. I'm going to let you guys do this on your own. Sebab banyak dah example kita dah go through and hopefully semua dah faham how to do it. Next subtopic is torque and angular acceleration. Now we know that F is equal to ma. This is our Newton's second law, right? And we know that A is equal to R alpha. Remember that we talked about V equals to R omega, S equals to R theta, A equals to R alpha. So these are the equations that we have learned previously. And it's asking us, hey, do you remember A equals to R alpha? Because we're going to use it in this equation. So they substituted, okay, they did not. They used torque first. So torque is equal to RF. So sama macam S equals to R theta, V equals to R omega, A equals to R alpha. They said torque can be related to F by T equals to RF. But I want you guys to really notice something here. Over here is your rotational. Kenapa saya pakai crayon ni? Saya tak faham. Over here is your rotational parameters, rotational stuff lah, rotational, what do you call it, terms. This is your linear terms, linear. But this guy, semua ada connected by R. All of them are connected by R. This guy is your rotational, dia terbalik. This is your linear. It is connected by R, yes, but terbalik. So please take note, SVA, the equation sama, R theta, R omega, R alpha, torque je yang special. By special, I mean menyusahkan kita lah. So torque is equal to RF. Okay, you need to remember this. It's the only guy that is different. So torque is equal to RF and we substitute F to be MA. So RMA, this is linear acceleration. This is just substitution, don't panic. So A is equal to R alpha. Masuk lagi, R alpha. So now we have mr squared because we have two r's here and it becomes alpha. Now this mr squared, we combine this to become I, where I is called the moment of inertia. So this is our new term, moment of inertia. So if you look at this equation, torque is equal to I alpha. It kind of looks like MA, F equals to MA. It kind of looks like that. And it is related. So torque is equal to I alpha. This is another equation. The other equation that we used previously was torque is equal to R cross F. RF sine theta or RF perpendicular. This was our first equation that we used for our free body diagram and to determine whether something is in rotational equilibrium or not. This is another equation. Torque is equal to I alpha. So your second equation. Torque is equal to I alpha, where I is the moment of inertia, alpha is your angular acceleration. It kind of looks like F equals to ME. Okay, so what is moment of inertia? We're going to talk about that. So this is number 2. Okay, so any questions so far? Is everyone okay? Still awake? It's okay. Thursday, not Friday yet. Yes, okay. So everyone's okay kan? Kalau soalan, please interrupt me as usual. Okay, next one. So net torque for a rigid body. In rotational motion, each particle moves in circular path. Each particle moves in a circular path, but with different radius. I've demonstrated this to you guys before, previous class, but with the same angular displacement, angular speed, and angular acceleration. So I'm going to repeat myself here. I'm going to do slideshow. So we start with this triangle, right? And we take a few particles in this object as our reference point. So we have, this is our axis of rotation. It's going to rotate about its axis. It's going to rotate over here. Oops, there's that block. It's going to rotate over here. Our two particles that we want to refer to is this yellow dot over here and also this red dot. Okay, so now if I start rotating this triangle anti-clockwise. Anti-clockwise is this way lah, terbalik dari arah jam. So it would move like this at its center. So as you can see over here, the axis of rotation does not move. Even though I rotate it, the axis of rotation remains there because itu adalah paksi kita. So apa-apa sahaja pergerakan rotational, paksi dia takkan berubah. You can imagine it like the clock. Dia akan jarum clock tu akan bergerakkan in rotational motion. The only part that is not going to move is tengah-tengah tu. Dot tu remain there. It's not going to move anywhere. It is rotating. It supports the rotational motion, but that dot remains over there. No translational, no angular displacement. It's there. Okay. So you can see over here the axis of rotation does not move. I mean, yes, it supports the rotational motion, but it is still there. It's not going to berubah tempat lah. Paksi kita takkan berubah. So our yellow dot moves this way and the red dot over here now is over here. They look as if they are not connected at all, right? However, they are connected by the same angular displacement. This dot moved by some angle. This red dot also moved by some angle. That some angle is actually the same angle, but they look different because they have different radius to the axis of rotation. Now try to imagine this as if we're talking about torque equals to Rf. Imagine that the particle is our F, this is the radius. This is our F, this is the radius. They have different radius. But if I rotate this triangle, they all move at the same theta, but they have different radiuses. So they would contribute differently lah. So let's see what the angle is. Oh, we have 3 particles. Saya tak perasan yang ni. So it continues moving. Sorry, let's go back. So as you can see here, the angle over here is going to be the same as the angle over here. Is going to be the same as the angle over here. Nampak macam tak sama, but it is actually the same. And it continues to rotate. Rotate and rotate. So the axis of rotation remains over here, even though these particles dah pergi mentah mana-mana, dah enjoy second. Okay, so you can see over here that the radius plays an important part in showing us what happens over here. So torque is dependent on radius, we know that. But even though they have different radiuses, they move in the same angle. So if we have the same theta or angular displacement, we would have the same angular velocity. We would also have the same alpha because the rate of this guy is this guy. The rate of angular velocity is angular acceleration. Okay, we talked about this previous class. I'm just recapping here. Okay, so what does this have to do with moment of inertia? Okay, I'm getting there. So for a rigid body, all points on the body has the same angular acceleration. Kenapa? Sebab dia bergerak pada angle yang sama. Angle yang sama, angular velocity yang sama, angular acceleration yang sama. They are connected. So we can say that for a rigid body that is rotating, all the points in the body has the same angular acceleration. Then we can write the net torque as mr squared net. in the mr squared alpha. Kenapa ada net ni? It is referring to all the different particles. Pengsan nak kira semua radius ni. So setiap particle ni, they have their own radius. They have the same acceleration, they have the same angular acceleration, they all have the same rotational acceleration, but they all have different radiuses. So how do we account for this torque? I don't want to account for that. It's going to be tiring. So we have like, I don't know how many atoms here. Do we want to do all that hard work? No, let the physicists do that for us, or let the mathematicians do that work for us. They said, okay, so let's integrate this. Let's integrate this, use math to make our life easier. We don't have to calculate all the radius of these particles. We're gonna say net in mr squared, and we're gonna call this as I, and I is dependent on the shape of the object, the weight of the object, and also the mass of the object, the shape, the size, and the axis of rotation. Kenapa semua benda ni penting untuk tentukan moment of inertia? Sebab kita ada sebelambak partikel, we need to know what is the axis of rotation to know the radius. Betul tak? The axis of rotation tells us the radius. The size of the object tells us the radius. The shape of the object tells us the radius, and the amount of particles in that thing, the mass of the object, tells us how many particles are in that object. So all of this contributes to the moment of inertia. I know. Macam, kenapa nak kena buat benda susah ni? Tapi tak apa, diorang nak kasih kita solution. It's called I. So we don't have to integrate. Yay, lucky us. So it's called I. So let's go back. So all of these things, mass, shape, axis of rotation, contributes to the moment of inertia. Moment of inertia is mr squared, right? The mass, the radius. Okay, so everyone's like, alamak, tak nak belajar dah. Sabar-sabar. Kita dah sampai solution dia. So mr squared, I is equal to the net mr squared is called the moment of inertia or rotational inertia of an object. These two objects have the same mass. We can say that this guy is 10 gram, this guy is 10 gram. However, remember that I is equal to net mr squared. So the radius with respect to the axis of rotation is different. So obviously, even though they have the same mass, they won't have the same moment of inertia. So for a single particle, the moment of inertia is only a single particle, assuming this is like a single particle lah. So we only have one mass and one radius. We have like we have 4 particles over here. This tells us, hey, you need to calculate for all 4. So it's going to be m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus m4 r4 squared. This is going to be our I. And for this guy, orang cakap give up je lah buat integration. So this is r squared with respect, integrating r squared with respect to m, So if we integrate this, it becomes mr squared. Still, tapi ada axis dia lah, tak tahulah axis dia apa. Axis pula. Limit. I don't like math. Okay, I shouldn't say that. Yes, I like math. Okay, next. Okay, so to make our life easier, let's just memorize this table. If you don't want to memorize, you have to integrate. So let's just memorize. I would rather memorize than integrate. Okay, so for a thin hoop with radius capital R, kenapa gambar dia macam tak clear? So for a thin hoop with radius capital R, the moment of inertia is m, referring to the mass, r, referring to the radius of the thin hoop. And then if this is the axis of rotation, by the way. Okay, so the next one is also a thin hoop, but the axis of rotation is over here. The lain, axis of rotation lain. Remember, the axis of rotation determines our R. So now instead of the R over here, our R is now here. Dia macam dia macam lain lah. Their values are going to be different. So now we have, this is width W, the width of this loop. Saya pun macam give up tengok benda ni. Sebab macam banyaknya nak kena hafal. Tapi hafal lagi senang daripada integrate. So hafal lah kita. So this is our axis of rotation. This is our R. This is our axis of rotation. This is our R. This is the width of this thin hoop. Assuming that it has some width. Yang ni kita assume dia macam kecil. Dia sangat-sangat nipis. Yang ni kita assume dia nipis tapi lebar dia ada. So it has some width. So 1/2 mr squared plus 1/12 mw squared. Okay. And then the next one is solid cylinder. We have a solid cylinder of radius r. So it's just 1/2 mr squared, and a hollow cylinder. This is the cylinder tapi sekarang dia hollow. So it has inner radius r1. Dalam ni ada radius 1 and then kat luar ni radius nombor 2. 1/2 mr1 squared plus r2 squared. So for the time being, if you can't remember yet, it's okay because web assign nanti boleh practice through these things. Hopefully by then you guys can remember. Tapi kita buat exam pun online kan? So, you know, macam lah saya tak tahu korang tengok buku kan? Ada yang tengok buku. So I don't think anyone memorized anything, any equations so far. Kalau ada baguslah, but you know it's online, right? And then we have ada lagi. Okay, we have the uniform sphere of radius r, 2 over. Kenapa lah tak jelas ni? I don't have my book right now. I think this is 5. Think so. 2/5 mr squared. This is in your book, by the way, so you don't have to rely on my slide. And then this is 1/12 ml. The L is over here. 1/3. Now remember, this is the axis of rotation. This is the axis of rotation. So they have the same shape, but they rotate differently. Satu rotate kat tengah-tengah ni, satu lagi rotate kat tepi. Then this guy. So you have to know to differentiate the axis of rotation. Tengok jadual ni betul-betul. Axis of rotation kat mana? Ada width ke tak? What is the radius? Do they have 2 radiuses? Satu dalam, satu luar. Those are very, very important. Okay, so that table you can go through it again yourself. Let's go through this example. Do we have more time? Can we take like a 2-minute break? Because I'm tired. I need some drink. 2 minutes. Ada soalan boleh tanya So 8:40, let's come back. 40 AM. Kejap saya nak ambil air. Good morning. Ada soalan tak? No questions? Okay, so let's continue. Where was I? Okay, buat soalan ni. Oh, laju juga saya. Saya tadi turun tangga ambil air 2 minit je. That's impressive. Okay, next one. So 4 objects are held in position at the corners of a rectangle. So ada 4 objek di sini ataupun 4 particles. You can see that. Of a rectangle by light rods. Sekejap. Are held in position by light rods. Oh, okay. So it's saying that benda ni dia tak adalah tiba-tiba muncul tergantung kan. They are held in position by light rods. Rods yang sangat-sangat ringan. By ringan, they meant to say you can ignore the moment of inertia. So moment of inertia, I is equal to mr squared, right? So if our mass is negligible, if our mass is like not significant, we can just say there's no moment of inertia. So that is what they meant by light rods. They could have just said string though. Okay, never mind. Of a rectangle by light rods as shown in the figure. Find out the moment of inertia of the system about the x-axis and also about the y-axis. Let me duplicate this. So we have space. Duplicate and then I'm going to remove this. So how should we do this? Okay. So we are going to use the moment of inertia. Remember the moment of inertia is mr. I is equal to net in the mr squared. M is mass, R is the radius. What radius? Radius with respect to the axis of rotation. Now, did they tell us where it was rotated? Yes. Find the moment of inertia of the system about the x-axis. So this is our axis of rotation. This is what they mean. So if our x-axis is our rotational, it's going to rotate about this way, it would move this way, right? Okay, macam nak bayangkan Do I have anything to show? I have a pen. And I have this card. Okay, so let's assume, why is this card not showing? Lah, kenapa macam tu? Kalau letak kat badan saya pun tak nampak. Okay, this is the axis of rotation. This is our x-axis. Okay, please look at me. Oops, it's not drag me. So this is my axis of rotation, right? This is my x-axis, and this is the 4 particles over here. 4 particles. So if they said this guy is moving about its x-axis, it means to say that it's going to move like this. Okay, so this guy is going to move like that. Macam tu. Okay, so that is x-axis. So everyone got that? So the next one is it's going to move about its y-axis. So y-axis is over here. So this is my card, the same card. The 4 particles are on each side. So now my rotation is in the center. So if this guy is going to rotate, right? It's going to rotate. Hello. It's going to rotate. So it will rotate like this. Macam mana saya tahu dia rotate macam ni? This is my axis of rotation. If this thing is, saya lekatkan dengan gam, saya pusing benda ni, dia pusing macam ni lah kan? Dia akan pusing macam ni. If it is about the y-axis. And again, if it was at the x-axis, saya lekatkan gum kat sini. This is my, where I twist anything, this is my paksi lah. So it's going to rotate like this. Okay, you can imagine it like that. Alright, so use your random objects in the house if you can't imagine well. No one is stopping you. Okay, you can use whatever is in your pencil box. So that is how I like to do it. I'm imagining it first. So we have 2 situations here. The first one, the axis of rotation is the x-axis. The second one is the y. Okay, so let's move on to A. So A is find the moment of inertia. So I at about the x-axis is we have four particles: particle number 1, particle number 2, particle number 3, particle number 4. Now I want you guys to help me. Tell me the radius for each particle. So let's talk about particle number 1. Particle number 1 has mass of, let's write the equation first, m1 r1 squared, m2 r2 squared, m3 r3 squared. I know I told you guys like boleh memorize equation, right? But if they give us something that is not in the table, we have to do this. So sorry. So saya patut ada disclaimer tadi. Kalau tak ada dalam table, kena buat sendiri. Okay, so what is my M1? It is 5 kilogram. What is my radius for M1?
2.
Berapa?
2.
2
4.
or
3.
3.
kejut saya. Kenapa 4 pula? Okay, so 3 So why is it not 2?
Sebab
It's rotating
to
through the
Y.
x-axis.
Center is X.
We always have to define our axis of rotation. The radius is with respect to the axis of rotation. Correct. Okay, so everyone got it. So this is going to be 3 squared. Okay. Next one, M2, 2 kilogram. What is my R?
3.
3.
3.
Okay. M3 is 3 kilogram. What is my R?
0.
0. Yes. This is the part where people usually make this mistake. Diorang akan macam cari juga length. Padahal it's on the axis of rotation. So it's going to be 0. So this is going to be 4 and also 0. It's on the axis of rotation. This entire thing is the axis of rotation. Boleh. Because it's the, we saw that this is our axis of rotation. It was the whole thing. So this is going to be 0. Okay, so now we have 5 times 9, 45, 2 times 9, 18, 3 times 0, 0, and 0. So 4, 5, 50. No, it's going to be 63. Good. Hopefully betul lah. And I forgot what the unit is. So M is kilogram, R is meter. So meter squared, kilogram, meter squared. Let's see the table. Does it mention the tak bagi unit ke? Shush. Ada tak dalam buku korang? Like they specify unit dia apa? We can do it ourselves, but
Square.
kilogram meter squared. Macam tu je.
Square. Yes.
Okay. So I'm assuming they just use this equation. There's no other like substitute ke apa ke. So M is kilogram, R is your meter. So meter ni squared. So you got kilogram meter squared. So don't forget your units. Okay. So that is how you do for part A. Part B. Let me make this smaller. Okay. Group this. Okay. So part B, let's do this in another color. So now our axis is over here. Ooh, our axis is over here. And again, I have to write the equation. M1R1 plus M2R2 plus M3R3 squared. Squared. M4R4 squared. You don't have to write this. I'm just showing it to you guys. So M1 is M1 is 5. What is my R over here?
2.
2 squared. M2 is 2 kilogram. What is my R?
2.
2 squared. What is my, M3 is over here, is 3 kilogram. What is my R?
2.
Still 2. And then we have our 4 kilogram and the R is still 2. So this is the R, this is the R, this is the R, this is the R. Okay. So now we have 5 times 4. Malasnya nak kira. 2 times 2, sorry, 2 squared is 4. 4 times 5 is apa? 20. 4 times 2, 8. 4 times 3, 12. 4 times 4, 16. 16, 12, 28, 36, 56. Hopefully. Okay. So they are different. They are the same, like it's the same particle, right? But the axis of rotation is different. So it would give you a different moment of inertia. So this example demonstrates that. Okay, moving on. So I hope everyone is okay. First, always determine your axis of rotation. Okay, so a grinding wheel is a uniform cylinder. So this figure is irrelevant. A grinding wheel is a uniform cylinder. Let's go for 5 more minutes before we end class. Grinding wheel is a uniform cylinder with a radius of 8.5 centimeter. Let me draw it. Please expect the worst. This is my cylinder. Oh, sorry, it's a grinding cylinder. Dia akan crush stuff into powder, right? So kalau kita nak grind something, kita akan letak dia macam ni lah kan. Takkan nak grind ke tepi pula kan. Kita grind macam ni lah kan. So kita letak macam kristal ke apa ke kat sini. Dia pusing-pusing sampai jadi powder. Okay, patutnya kristal macam ni jadi powder. Macam tu lah. Okay. Macam batu lesung. Okay, batu lesung is not a grinding wheel by the way. So a grinding wheel is a uniform cylinder with a radius of 8.5 centimeter. So 8.5 centimeter is our radius and a mass of 0.58. Okay, so 0.58 kilogram. Kenapa saya letak kat sini? 8.5 centimeter. Okay. This is our R. Okay, so the net calculate its moment of inertia about its center. So now this thing is not like separated into particles. We don't know how many particles we have here. We don't want to know. We just use the table. So it's a cylinder, but we have to define its axis of rotation first. So for a grinding cylinder, we know that is the aim ataupun the purpose of the cylinder is to crush objects into finer particles, right? So it has to move with this kind of axis of rotation. So it's going to rotate macam tu lah kan, macam tayar lah kan. So let's go back to the table. Do we have that in the table? We do have a solid cylinder of radius r and the axis of rotation is through its center. However, the orientation is different. Can we still use this equation or not? The orientation is different. Can we use it? Boleh ke tak?
Yes.
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 Doesn't really matter, right? As long as the axis of rotation is the same with respect to the object. So rotate je lah. Akan jadi saya ingat macam tu. So boleh pakai. So 1/2 mr squared. What is m? M is the mass. R is the r from the axis of rotation to the end of the cylinder. So that is our equation. 1/2 mr squared. So I is equal to 1/2 capital M r squared. R squared. Okay. So 1/2 M is 0.58 kilograms. So that is already in SI unit. Our R is 8.5. We need to make it into SI. What is this? 0.085 meter. Okay. So that is 0.085 meter squared. That is my moment of inertia. So it does make our life easy. Cuma kena ingat equation. Times 0.085 squared divided by 2. So as an engineer, I never care about equations, to be honest with you. I refer to equations when I need it. I don't really mind how it's derived. I just use it, and so the purpose of being an engineer is to make things work. So I use whatever knowledge yang orang lain dah buat. I don't care about being the smartest one in the room. I want things to like bergerak, berjalan. So that is how things are made by engineers. They use all the knowledge that they have from other people, they don't care about coming up with the new stuff. They use whatever that is existing, they combine it and make new stuff. That is how engineers work. So 2.09 times 10 to the minus 3, this is kilogram meter squared. So I'm just like pointing out the difference between physicist dengan engineering lah. Okay, so whichever that you like, you can go for it. If you want to do medicine, you can go for medicine. Pharmacist pun boleh, vet pun boleh, apa yang that makes you passionate. Okay, next one. B. The net torque that is needed to accelerate it from rest. So from rest to 1,500 RPM. What is RPM? Revolution. Is it acceleration? Is it velocity? Is it displacement? Which one is it?
Velocity.
It's
Velocity.
angular velocity, right? Angular velocity, what is the symbol ataupun term dia?
Omega.
Okay, so this guy, omega, walaupun dia cakap net torque needed to accelerate, but it is saying from rest to 1000 RPM. So this is actually omega. So omega initial is 0 from rest. Omega final is 1500 revolutions per minute. We have time? Oh, kita dah terlebih masa. In 5 seconds. So I'm going to write down the parameters. Kita akan sambung in next class. So it's asking what is the net torque needed to accelerate it from rest. So it's asking, we know that torque is equal to I alpha, right? So I kita dah cari, kita nak cari alpha pula. If it is known to slow down from 1000 RPM to rest in 55. Okay, never mind. We'll do this next question, next class. Dia kata tahulah saya. Okay, tak apa, next class So, does anyone have any questions before I switch this off? Have a great rest of the day, by the way. No questions? Okay, so if you have, please WhatsApp me or WhatsApp the group. We'll discuss it. If not, have a great rest of the day. Have a great weekend. I'll see you next week. Bye, guys. Don't forget WhatsApp.
Thank you, Doctor.
Doctor.
Thank you, Doctor.
Bye.